Okay, so let us continue our discussion on forced vibration. So, now if you recall, we solved the problem when we have a mass spring dashpot system and we excite that with a harmonic force. So, that is the system we consider: stiffness, then damping constant, and then there is a mass, and we apply a force that is causing the displacement x of t. So, the force is f of t, and the equation of motion is m x double dot plus c x dot plus k x is equal to f of t. And we consider two different types of forces. One is a constant force, and the second one, f t, is equal to f naught then sine lambda t. And the solution for this excitation is x of t is equal to a cos lambda t plus b sin lambda t. And also we estimated the constants a and b. So, a is equal to minus twice eta omega n lambda divided by omega n square minus lambda square whole square plus twice eta omega n lambda whole square, and then this is multiplied by f naught by m. Similarly, we have also obtained what is b. B is nothing but omega n square minus lambda square divided by omega n square minus lambda square whole square plus twice eta omega n lambda whole square, and then we have in the numerator f naught by m. And these two constants we obtain from the initial conditions. And once we estimate this, we can then write the expression for this response, and obviously in this case this is the particular integral. And if we want to find out the total response, we have to sum it up with the complementary function. So, that is fine. Now, if we can assume that omega n square minus lambda square is equal to r cos theta, and then twice eta omega n lambda is equal to r sin theta. Obviously, if we square them up and then sum it up, so we will get r square is equal to omega n square minus lambda square whole square plus twice eta omega n lambda whole square. And also tan theta will be equal to twice eta omega n lambda divided by omega n square minus lambda square. Now, if we apply this simplification and then we write down the expression for this particular integral, obviously what we will get here, we will obtain f naught by m, it will remain there, and what we have in the denominator. So, this will be omega n square minus lambda square whole square plus twice eta omega n lambda whole square, and then we can show that after simplification we will have r then sine lambda t minus theta. So, that is the response. Now, still we can do a further simplification. Now, if you can notice, r square is equal to omega n square minus lambda square whole square plus twice eta omega n lambda whole square. So, that means we can further simplify this expression. So, if we do that, then it will be f naught divided by m, and in the denominator we have omega n square minus lambda square whole square plus twice eta omega n lambda whole square, and the square root will be applied over the complete expression. And then here there will be sin lambda t minus theta. So, that is the particular integral. So, now we have the solution for the particular integral. So, if we sum it up, now obviously we have the response that you can see in terms of lambda and omega n. Now, we can further simplify this expression, that we will do in a minute. So, let me just sum it up and then write down the expression, and then further we will discuss how we can simplify this expression, and there is a very interesting phenomenon that we will study in a minute. So, what we have, the particular integral when we have a linear system and then we excite that system with the help of a sinusoid. So, what we have here, f naught by m sin lambda t minus theta, and then in the denominator we have omega n square minus lambda square whole square plus twice eta omega n lambda whole square. Fine. So, now you see we have a dynamic system whose natural frequency is omega n. So, if you see the expression, what is omega n? It is square root of k by m. So, if you know the stiffness and mass of the system, so we can easily calculate the natural frequency. And then we have lambda. What is lambda? It is the driving frequency. So, we have the forcing function here, and then that forcing function has a driving frequency which is lambda. So, let us define R, which is the ratio of lambda and omega n. Obviously, R, it is a dimensionless number. So, we have here the driving frequency, that is lambda, and then we also have the natural frequency of the system. Now, if you recall, what is k? K is nothing but m omega n square. Now, if you use these two expressions, obviously we can further simplify this response, and before that let me just write it down here. This is particular integral. Okay. Fine. So, what we will do? We have f naught divided by m sin lambda t minus theta, and then we can simplify the denominator. So, what we have here, if you see, we can take omega n square out, and then what we will have 1 minus lambda square by omega n square. So, this is r square whole square plus, in the next term what we have? We have, so sorry, there will be omega n square whole square. So, this will be to the power 4, and then what we have here is again omega n to the power 4, and then what we will have inside is twice eta. We take 1 omega n, so that will be omega n square, and lambda by omega n. So, this will be omega n square. So, if I take it out, that will be omega n to the power 4, and then inside it will be r twice eta r whole square. And then what we can do? We can take this omega n square common and then take it out of this square root, and then further simplification will give f naught divided by m omega n square. So, that is there, and then we have in the denominator 1 minus r square whole square plus twice eta times r whole square, then sin lambda t minus theta. Obviously, this omega n square here times m, we can replace it by k. So, that we will do now. So, what we can do here in terms of stiffness, we can replace this. So, k is equal to m times omega n square. So, that we replace, and ultimately what we get in the numerator is f naught by k. Now, if you recall, what is f naught by k? If I have a stiffness k and I apply a force f naught, obviously f naught by k will be the deformation x under which condition? The static deformation. So, we call it x of st. Now, if that is the case, we can further simplify. So, what we have here in the numerator, so this will be x of st. So, now you can see that what we have here, this term it is the amplitude of the response, right, because we have sin lambda t, okay, and the particular integral will have an amplitude of this term inside the box shown by this red dotted line. Now, if you further look into this expression, then what you can notice is that 1 by, there is a term 1 by 1 minus r square whole square plus twice eta r whole square. Now, r is a non-dimensional number. Also, eta, it is the ratio of the damping to the critical damping. We call it critical damping ratio. So, this is also dimensionless. So, this quantity what we have is actually a dimensionless quantity, and this is what we call DMF. Why we call it DMF? What is the full form of DMF? We call it dynamic magnification factor. So, this is DMF stands for dynamic magnification factor. What is the meaning of it? Just imagine if we have the stiffness only, that means it is a static case, and then if we apply the amplitude of the forcing function, which is f naught. So, it is a sinusoidal force, its amplitude is f naught. If I apply that, we will get static deformation. Now, the moment we introduce dynamics to the system, what will happen? This static response will be multiplied by this factor DMF, and the response will get amplified. We will plot this expression in a minute, then it will be further clear. But what we can conclude from this expression is that the amplitude of the dynamic response is actually static response multiplied by the dynamic magnification factor. Now, this dynamic magnification factor, even if you look at, it is a non-dimensional number. We will plot this expression in a minute. But before we plot, let us see what is the nature of the dynamic amplification. Now, just imagine if we have r equal to 0, then what will happen? If I put r equal to 0, obviously dynamic magnification factor will be what? DMF is equal to, if you can estimate, obviously this will be 1. Now, if we increase r, and if r is really very high, what will happen? If r tends to infinity, what will be the dynamic magnification factor? So, r going towards positive infinity, dynamic magnification factor will be 0. So, that is the nature we can conclude. And what happens when R equal to 1 or close to 1, you will see, and R equal to 1 and eta equal to 0. So, obviously, the moment we put eta equal to 0, the second term is 0, and because R equal to 1, 1 minus 1 square, which is also 1. So, this will be 0. So, 1 by 0. So, DMF will be equal to infinite. So, that is the nature of the dynamic magnification that we can easily conclude from the expression that we have derived. Out of that, the last one is, I just wish to draw your attention that the moment we have a system where there is no damping, and if we drive that system with a harmonic excitation and by chance the driving frequency is exactly the natural frequency, then what will happen, because the dynamic magnification factor is infinite, the response will be infinite. And such a situation is called resonance. I will show you some video of resonance also, which is again available in the public domain. It is really interesting. You will see how the resonance can actually destroy a structure. So, this is a very dangerous situation where we have damping is equal to 0 and we have R equal to 1. Now, obviously, when we have damping not equal to 0, obviously R equal to 1 and damping not equal to 0, then what will happen? The first term of the DMF in the denominator will be again 0 because R equal to 1, but the second term will be there. So, the DMF in this case, DMF is not infinite, it will be finite. And we will see how the response will look like in a minute, but at least from this expression we can conclude the main features of this dynamic magnification factor. So, now let us plot this expression. So, for that let me just create some space here. So, and then we will plot this expression and we will see how this dynamic amplification or dynamic magnification factor looks like. So, we have on the x axis we have R, that is the ratio of lambda and omega n. Then obviously, we have R equal to 1.0, and then when R equal to 0, what is the DMF? It is 1. So, this is our DMF and we have this value is 1.0. So, we have now, let us first draw when we have eta equal to 0. So, what will happen? It will start from 1 and obviously, as we increase the damping, as we increase the frequency ratio R, it will go towards infinite when R equal to 1. So, it will look like this. This is when eta equal to 0. Now, what happens when we have eta not equal to 0? Again it will start from 1 and then it will go to a peak value and then again it will go towards 0 as we increase R. So, this is where eta not equal to 0, right. Now, what we can see, it has a maximum value and this maxima occurs in and around R equal to 1. It is not exactly R equal to 1, we will derive that in a minute, but when R is equal to 1, that is what we call resonance. That means the driving frequency is exactly equal to the natural frequency of the system. So, what we get is the expression of dynamic magnification factor And we also qualitatively plot this dynamic magnification factor as we increase R, and we also change critical damping ratio. Now, the next question that we are going to answer, where is the maximum? It is not exactly at 1, it will be just in the close vicinity of 1, but not exactly 1. We will see that in a minute. And we will also derive what is this maximum value. So, that is our next task. Let us do that. So, we have D as our dynamic magnification, and that we have 1 minus R square whole square plus twice eta R whole square. Now, let us first differentiate. Sometimes it is also used by a different notation. So, let us differentiate dynamic magnification with respect to R. So, what we will get? We will get minus, sorry, just let me check the expression once more. There will be a square root, I just missed it. So, it is here. So, that square root will be there. So, it is minus 2 within bracket 1 minus R square whole square, then plus twice eta R whole square to the power 3 by 2, and then minus 2 square R times 1 minus R square plus 2 square, then eta square, then twice R. This is equal to 0. Obviously, what we get if we solve this expression, what we will get, R square is equal to 1 minus twice eta square. So, this is the expression. I leave it as an exercise for you. It is very simple. You do it and cross verify. So, what we get? R square. So, we can find out what is R. R is equal to square root of 1 minus twice eta square. So, this is the value of R where our dynamic magnification factor will have its maximum value. Now, again we can find out what will be the maximum value of dynamic magnification. That is very simple exercise. What we will do? We have the expression 1 minus R square whole square plus twice eta R whole square root of this term. What we will do? Let us substitute this expression of R in this next expression, and we will find out what is the maximum value. Again, in this case, I just write down the expression and leave it again as an exercise. We can derive it. I leave it as an exercise for you. You please do it and make sure that you get the right expression. So, this is the maximum value of dynamic magnification factor. I just redraw once more the dynamic magnification. So, what we had here, so it will start from 1 and then it will reach its maximum value and then asymptotically go to 0 as r tends to infinity. So, this is the maximum value. So, this is mu. So, r is equal to 1 and this value is also 1. So, this is the location of the maximum value of dynamic amplification, and the peak value you can also identify. Obviously, when we have eta much less than 1, then what will happen? Obviously, eta square we can neglect, and in that case R max is equal to 1. So, when we have very low value of critical damping ratio much less than 1, obviously this term eta square will be very small, and then we can neglect it. We will have maximum value of dynamic amplification at r equal to 1, right. And in that case, what will the maximum value? That also we can simplify. Obviously, if eta is much less than 1, this quantity we can neglect, and obviously the maximum value is 1 minus 2. So, this is only when we have very low value of damping. Now, out of this discussion what we can conclude is that if you have a linear system, then if we drive the system with a harmonic excitation, and by chance if we have the excitation frequency that matches with the natural frequency of the system, then resonance occurs. And if you have a very low value, if it is 0, then obviously the dynamic amplification will be infinite and no structure can actually withstand that. So, from that perspective, damping actually helps us to reduce this dynamic amplification from infinite to a finite value. Still, this value, which is 1 by twice eta square root of 1 minus eta square, still this value is very high, and at least the value, this value is more than the value of 1, and then in that case we can conclude that the dynamic response will be more than the static response. So, the moment we have dynamics, and if we need to design that structure, obviously we have to design the structure for the maximum amplitude of the dynamic response, and if you have more response, obviously we will have more strain, and more strain means more stress. So, we have to design it accordingly. But the point is that once we have a linear system, we drive that with a harmonic excitation. In that case, we have derived the solution, and before I conclude, if I write down the complete solution. So, what we have x of t, which is the total response, is equal to e to the power minus eta omega n t c cos omega dt plus d sin omega dt, and today we have derived the other component, that is the particular integral, which will be of the form x s t times dynamic magnification factor times sin lambda t minus theta. So, that is the total response. Now, again I repeat, the moment you find out these two constants, you have to consider the complete response, and once you get the complete response, you apply initial conditions and then find out these two constants C and D. A common mistake is that use the previous expression when we have free vibration, that is wrong. So, you have to consider the complete expression and find it out. So, with that, let us close here. In our next class, we will continue from this point onward. Thank you very much.